Okay, I think we can start. Very good morning to all of you, and welcome to the second part of the lectures on astrophysical jets and supermassive black holes. Okay, so today we'll try to cover a little bit more than what we did yesterday, but I would like you to be still very interactive, and I will post questions, and depending on your answers, we'll keep going ahead. Okay, yesterday we saw the jet in the famous elliptical galaxy, Messier 87, M87, as it is popularly called in the Virgo cluster of galaxies. And we saw how the jet has been studied across the electromagnetic spectrum from the very low frequency radio waves to the highest energy gamma rays. So today we'll start by posing the question to ourselves that, that when we see these jets, what is the radiation process? Which physical processes are responsible for the emission? Okay, the emission, and what are the diagnostics? How would you find out what is the nature of emission? How would you go about it? You can make an image of the radio jet, as we saw. You've seen images of the jets in M87. So some quick answers, either by unmuting yourself or putting your thoughts on the chat. Anybody? Nobody? You've listened to the lectures on radiative processes, and how would you go about finding out which is the physical process which is responsible for the emission which you're seeing in jets in active galaxies? So you have to respond. Okay, there's a chat response over here. Who can Bremstrahlung? Okay, Anudeep saying synchrotron radiation. Vidyut Haldar says. Anudeep says Bremstrahlung. Vidyut Haldar says synchrotron radiation. Anybody else? Another quick answer. Do you agree or disagree with them? Or if you
Hello, sir. Am I audible?
You're audible, sort of.
Okay, sir. So can I try? Basically, actually, the jets from a black hole forms like when the matter is going around the black hole.
No, I'm asking for what is the radiation process. I'm not asking how the jets arise. When you see emission, there has to be a physical process responsible for the emission. What is the physical process is what I'm asking. There are two answers so far, Bremstrahlung and synchrotron radiation. How would you, for example, suppose it was one of these two, how would you go and distinguish the process? Okay. Any other quick answers? No? So we will try and discuss this briefly and then we'll move forwards. Okay. Now, let me first just briefly recap how you would go about it and just briefly recap synchrotron radiation. Bremsstrahlung, I will not get into because thermal Bremsstrahlung is not the physical process which is responsible for the emission which you see at from these very extended radio jets. Okay, I mean, you can get Bremsstrahlung emission from active galactic nuclei, but usually from the extended radio jets extending to kiloparsec scales and all that, or tens of kiloparsec scales, it is not the Bremsstrahlung. Okay, we look at the two processes and we'll see how to distinguish between them and what is and how do we go about it. Okay, now the main process which Vidyut Halder mentioned is synchrotron radiation. What is synchrotron radiation? It is ultra-relativistic particles moving in a magnetic field. So we know that the plasma is highly relativistic. So particles are moving at almost the velocity of light. They are accelerated in a magnetic field by the Lorentz force. And what happens is that you're familiar with cyclotron radiation, which is mildly relativistic electrons or charged particles moving in a magnetic field. But when you transform these particles, when you consider highly relativistic particles moving at almost the velocity of light, the transformations lead to the emission being a narrow cone of emission. with a half angle of theta, which is equal to 1 upon gamma. Gamma is the Lorentz factor of the individual electron, not the gamma factor of the jet itself, but the Lorentz factor of the individual electrons. Now, what would a distant observer see? Because it is coming as a pulse and the electron is moving around it, what the distant observer will see pulses of radiation when the cone sweeps his or her line of sight. And what will he see it at? He'll see it at he or she will see it at the Doppler shifted gyration frequency, and you'll also see all harmonics. Okay, spectrum at all harmonics of nu g, the gyration frequency. And the harmonics are closely spaced, and what you see is a continuum of radiation from a single electron. What I'm talking about right now is a single electron moving in a magnetic field. The sketch over there says the electron moving in a magnetic field gives rise to X-rays, but at what frequency it is going to emit will depend upon two things. One is the energy of the electron itself, and the other is the strength of the magnetic field. So the energy from a single electron peaks at roughly 4.2 gamma squared, and the perpendicular component to the magnetic field. So I've just given you one number over there, which is that if I have an electron with a Lorentz factor of 10 to the power of 4, okay, a Lorentz factor of 10 to the power of 4 would correspond to an electron, say, moving with a velocity of about, you can see 0.999999999 c. And when this moves in a magnetic field of 10 microgauss, it will emit a maximum energy at 1 gigahertz. Now, 1 gigahertz is in which region of the electromagnetic spectrum? A quick answer. Quick answer in the chat. Where does 1 gigahertz lie in the electromagnetic spectrum? No answers? Quick answer. Okay, there are two chats over there, microwave, gamma, or X-ray. X-ray, no. 1 gigahertz is in the radio region of the spectrum. Okay? Okay. You have heard about quite a bit, radio. Amit Kumar did it very good. Because you have heard about a 21 centimeter line, which has been talked to you quite a bit. That's at 1400 megahertz, 1420 megahertz, which is at a wavelength of 21 centimeters. Okay? So you can translate nu equal to c lambda 1 gigahertz and convince yourself that this is in the radio region of the electromagnetic spectrum. Okay. Now, for example, if I want to emit in the X-ray region or the ultraviolet region, then you can see that the dependence on gamma is much stronger than the dependence on B. And if you have much more highly energetic electrons, for example, if it was 10 to the power of 8 rather than 10 to the power of 4, then you can see that you'll have to multiply this by 10 to the power of 4 squared. So 1 gigahertz is 10 to the power of 9 hertz. And you multiply it by that by 10 to the power of 8, you'll get 10 to the power of 17 hertz. And that will be approaching the X-ray region of the electromagnetic spectrum. So higher energy electrons would radiate at higher energies, and when you want to go into the highest energies, you need the highest values of the Lorentz factors. I've given this for a typical magnetic field in radio jets of about 10 microgauss. In the extended jets, if you were to consider nuclear jets, the magnetic fields have been estimated to be larger than that. Okay, but this is the typical magnetic field for the extended kiloparsec or 10 kiloparsec or 100 kiloparsec scale jets in active galactic nuclei. Now, you can ask yourself that I've considered only a single electron now, and what would the total spectrum look like? What is the spectrum? A spectrum is when I plot the intensity or the flux density versus frequency. And you can see that if I plot that on a log-log scale, for these extended emission, whether it be the jets or lobes of radio galaxies, that you will get a power law spectrum. Okay, what does a power law spectrum mean? That if you plot on a log-log scale, log s versus log nu, you will get a straight line. Now, if you want to get a straight line, what you measure as s is proportional to the power of minus alpha, then what you need is a power law distribution of the electrons itself. Okay. Now, what we talked a little while earlier was that the frequency at which an electron radiates is proportional to gamma squared. and be perpendicular. But gamma squared is a reflection of the energy of the electron. So lower the frequency, lower the energy of the electron. And if you have more flux density at a lower frequency, as shown in the plot over here, you have a larger flux density at a lower frequency, then you need many more electrons to add up because to give you this particular slope. And so you need a power law slope of the electron energy distribution as well to give you a power law spectrum of the flux density. For example, if P is equal to 2 over here, you'll get a spectral index of 0.5 because alpha is equal to P minus 1 by 2. This basically comes from synchrotron theory, which we have not done in detail, but it is enough for you to know that the optically thin part, that means where radiation is not getting absorbed in these synchrotron emitting sources, whether it be the diffuse halo in our galaxy, whether it be jets in active galactic nuclei, or the radio lobes in radio galaxies, that they tend to have a power law spectrum over a large frequency range. And this is related to the way the electrons get accelerated, which we will not have time to get into, but about various acceleration processes, Fermi acceleration processes, shock acceleration processes. These can give rise to power law distribution in electron energy distribution, and that is what we are seeing over there. So once you see a power law distribution of electron energy distribution like this, you know that it is not a thermal process like a Bremsstrahlung or a blackbody emission. Because the blackbody emission and the thermal Bremsstrahlung emission have quite different spectra. It is not a power law in this kind of form with a steep spectral index, which I've illustrated over here. The other thing to realize is that the higher energy electrons will radiate energy, all right, will radiate a higher frequency, all right, but they also radiate energy much faster. And the rate at which they radiate is proportional to the square of the magnetic field as well as square of the energy. So you'll find that the high energy electrons, unless they're replenished, will lose energy much faster, so that when you look at the spectrum will begin to steepen initially at higher frequencies. And with time, unless there's a replenishment of the high energy electrons, that sort of break or the steepening will move gradually to lower and lower frequencies. The other aspect to realize is that synchrotron radiation is due to radiation of highly relativistic electrons gyrating or moving in a magnetic field. So as long as there is an ordered component of the magnetic field, you'll also get linearly polarized emission from synchrotron radiation. So both linear polarization, detection of linear polarization, as well as the spectrum are signatures by which you can try and identify that the radiation process is due to synchrotron emission. Radiation can be depolarized. If there is time, we will see how that occurs when it goes through a magnetoionic medium. But basically, the field lines are completely tangled up rather than having a regular component. Then also your polarization is going to drop dramatically, depending upon the degree of the random component of the magnetic. When you make observations, um, you'll find that the lobes of radio sources, the large radio sources, can be polarized up to about 70% linearly polarized or so. And this is close to the theoretical limits of the degree of polarization that you can have for an optically thin emission from a radio source. Okay, so I know it's a little faster I'm going, but I'm not trying to get into mathematical derivations, but just illustrating to you the basic concepts that synchrotron radiation, if you remember, is just the energy due to highly relativistic electrons, ultra relativistic electrons moving in a magnetic field, and usually tends to have a power law spectrum, and the frequency at which it emits is higher for high energy electrons, and it is proportional to the square of the Lorentz factor of the electrons. Okay, and the rate at which it loses energy is also proportional to the square of the energy and also the square of the magnetic. So if you have a stronger magnetic field, it's going to lose energy faster. So these are all related to the physics of the radio jets and understanding what is the process by which radio emission or emission at high energies that you see. You need very high energy electrons to see synchrotron emission at X-ray energies, for example. We just saw that is proportional to gamma squared. So you need fields, Lorentz factors of about 10 to the power of 8 or so. Okay. The other important process is what is called inverse Compton scattering. Normally, one encounters in a regular physics course Compton scattering, where a photon interacts with an electron at rest or so, and the photon loses energy and the electron gains energy at the expense of the photon. But in these galaxies and in these highly energetic high energy astrophysics, in these active galactic nuclei, what you have is the electrons are moving about, zipping about at highly relativistic speeds. We saw that these electrons need to be about gamma to the power of 4, gamma to the power of 8. So they're moving about with quite high velocities. They will obviously have a whole range because you also have a whole range of the energies of the electrons. Now, what happens when the electrons are zipping about is that a low energy photon can scatter with the electron, which is moving with a higher velocity, and then it gains energy at the expense of the electron, and the photons are kicked up to higher energies, which can be responsible for the X-ray emission or gamma ray emission. So these processes are called inverse Compton scattering. So as I mentioned a little while ago, a photon of energy nu after scattering with a relativistic electron of energy E, which is equal to gamma me squared, MEC squared, where Me is the rest mass of the electron, then has a frequency nu IC equal to gamma squared of the order of gamma squared nu. So you can see that it gets scattered by a large factor, by gamma squared. For example, if you had a photon of 1 gigahertz, which you talked about earlier, and you had electrons of gamma squared 10 to the power of 4. So you can see 10 to the power of 4 squared is 10 to the power of 8 multiplied by 10 to the power of 9, which is 1 gigahertz. 8 plus 9 is 17. So the radio photon of 1 gigahertz gets upscattered to about 10 to the power of 17 hertz. Okay. So this is another very important process which is responsible for, particularly for the high energy emission. Now you can ask yourself that you have the electrons, you have the photons, which is the process which dominates? And that depends on the energy density of the photons versus the magnetic energy density. Okay. And that is all you need to conceptually understand. That obviously you need a greater photon energy density for inverse Compton scattering to be important, whereas synchrotron uh, radiation to be important, you need a higher magnetic energy density. Okay. The ratio of the luminosities is given by the LIC upon LS is just the ratio of the photon energy densities to the magnetic energy densities. The photons can come from the radio source itself or from the source of emission itself, or also it can come from the cosmic microwave background radiation, whose energy density increases with redshift. So it becomes, the inverse Compton scattering becomes more important as you go to higher redshifts. But you'll find that both these cases become important depending upon the physical situation that one you're dealing with. So in terms of the radiation processes, what we have are synchrotron emission and inverse Compton emission, which is responsible for the emission which you see from jets in active galactic nuclei. And we shall see in a little while that both these processes are important, but it varies from source to source, and we'll see that in a very short. Okay. The other aspect I just wanted to mention to you was that we talked about these jets supplying the lobes with energy, and you have a huge amount of energy stored in it. Okay. Now, what is the amount of energy? So that is, it was initially when these calculations were done by Burbage and his collaborators that one began to realize that the energy contents are extremely large. Okay, and the way they went about it, or the way we go about it today to get an estimate of the energy content in these lobes, is that we want to estimate the energy in the particles and in the magnetic field. Those are the two main constituents from the radiation which we observe. And what we see over here, what I've written over here, is that the energy on the electrons, energy of the electrons, is proportional to L b to the power of minus 3 by 2. Okay. Now, let me just give you a physical intuition without getting into any detailed derivations of it. This particular expression comes from synchrotron theory, that if I had a source of a particular luminosity, okay, luminosity, the luminosity is a combination of both due to highly relativistic electrons moving in a magnetic field, right? That is synchrotron emission. So if I have a lower magnetic field, then I need more energy in electrons, right? So that is why there is an inverse dependence over there. UE is proportional to L b to the power of minus 3 by 2. So, and you know that we know only of the electrons which are radiating, because it is more difficult to accelerate the protons to high energies. So most of the synchrotron emission is due to either electrons, is what we believe. There could be electron positrons as well. But we also have protons and ions in the plasma, because you can't achieve charge separation over those distances, so it will be electrically neutral. So there is a proton electron density, particle density as well. So the total particle energy, we put a fudge factor of K, so that to take care of protons and ions. And then we know that the magnetic energy density is given by b squared upon 8 pi, right? That is standard physics, which you know about. So that the total energy is given by proportional to KL b to the power of minus 3 by 2 plus b squared by 8 pi, which is the magnetic field energy density, multiplied by the volume to give you the total energy in the magnetic field. If you plot these two parameters, what you get is on the right over here, where the particle or the electron energy density particle goes down with magnetic field, and the magnetic energy density goes up. This comes from basic physics of b squared upon 8 pi. And you find that when you plot these, there is a minimum. So there is, and in this minimum value, there is rough equipartition between the magnetic energy density and the particle energy density or electron energy density. If I actually do these sums, I need to calculate the total luminosity in the radio region, for example, if I'm interested in the radio region, which I have taken from 10 megahertz to about 100 gigahertz, okay? And then I get a luminosity of about 10 to the power of 45 ergs per second. This is for the well-known radio galaxy Cygnus A, which we mentioned yesterday. And if we do these calculations, we get the minimum energy density, the minimum energy equivalent magnetic field is on the order of microgauss level. This is about 10 microgauss. This is about 100 microgauss. And the total energy in the part in the is about 10 to the power of 60 to 61 hertz. So there is a huge amount of energy which is being generated, in the nucleus of the active galaxy and is being transported outwards. Okay. So Ritter has asked the question: do the jets comprise of inverse Compton scattered photons only? The answer is no, and we'll come to it in a very short while. Okay. Come to that in a very short while. I'll show you some pictures as well. Now, let's go and just recap. Okay, radio emission, which you see, how would you find out what is emitting? To get to what Subrata Sarangi has asked, that do they consist of inverse Compton photons? Now, I can look at the spectrum across to look at what the emission process is. I will look at a broadband spectrum ranging from the radio region at the low frequency end to the higher frequency ends at the X-rays and gamma rays. X-ray polarization, is beginning to be done and will happen more extensively in the future. But right now we rely largely on the spectra and polarization at radio and optical wavelengths, and also the spectra which extends to X-ray wavelengths. Now, when we look at the radio part of the spectrum, which is the low energy part of the spectrum, then it is almost entirely synchrotron emission. In the optical region also, it is almost entirely from the spectrum and polarization, we infer it to be due to synchrotron emission. X-rays and higher energies, there is a component of emission in the low luminosity Fanarov-Rayleigh class 1 sources, where the spectra actually are contiguous in the sense that you have almost a continuum spectrum from where? From the radio region to the X-ray region of the spectrum. Because the spectrum is continuous, we believe that it is the same radiative process which is operating in these low luminosity Fanarov-Rayleigh class 1 sources, which is synchrotron emission right from the low energy radio photons to the high energy X-ray photons. because it is nothing but an extension of the relativistic electron spectrum from radio to X-rays and optical in between. Okay, and as we mentioned earlier, that when when the magnetic field energy is greater than the photon energy density, synchrotron radiation is a major contributor. And in these low luminosity sources, which are relatively nearby as well, most of them, the inverse Compton is not a major contributor. But when we go to the high luminosity sources, the situation changes. Here I've shown you the jet of a radio galaxy, Centaurus A, which is one of the very nearby radio galaxies. The contours are false colors. Okay, and what you see as X-ray emission, which is given in color, and the yellow contours are the radio contours. What you can see over here is that there are individual lumps of X-ray emission, and if you calculate the synchrotron lifetime of these electrons over here, that they're extremely short from the average magnetic field that one estimates. So there has to be local reacceleration of particles by shocks, etc., as the jets propagate outwards. But this kind of low luminosity jets we can understand largely in terms of synchrotron emission, a continuum spectrum extending from the low energy radio region to the highest energy X-ray region. The kind of spectrum which I illustrated to you when we were discussing synchrotron emission. But when we go to the higher luminosity sources, we find that that is usually not the case. For example, if you look at, I should have put a spectrum over here. For example, when you go in energy, you'll have radio at the low end, then optical, then X-rays. Now, if there is a dip in the X-ray, in the optical, and then you have a higher X-ray emission, then it is very difficult to understand it in terms of the same or similar population of electrons which are radiating from radio to X-rays. So then the other aspect which becomes important is inverse Compton scattering. Inverse Compton scattering can happen with the radio synchrotron photons as well as cosmic microwave background radiation. When you do the detailed physics of it, you'll have to take account of the fact that jets are moving at relativistic velocities, and so the energy density which it sees will be enhanced by a factor of gamma squared, okay, depending upon how fast the jets are moving out. And so in these high luminosity sources, inverse Compton scattering is believed to be playing an important role, although there are issues in terms of detailed modeling, but it is an important process which takes place. So both synchrotron radiation as well as inverse Compton radiation plays a role in the wide spectrum of jets in active galaxies. To answer Subrita's question, but what happens is that at low energies, at radio frequencies, it is synchrotron emission. At the higher energies, it's a combination of both synchrotron emission and inverse Compton emission, depending on the source and the particular physical conditions. Okay. So far, I've talked to you about linear jets, but I just wanted to give you one or two examples of jets which are curved because the parent galaxy it need not always be stationary. The parent galaxy can be moving about if it's in a cluster of galaxies. In a cluster of galaxies, the velocities of the parent galaxy, could be hundreds of kilometers per second, thousands of kilometers per second as well. And because they're all moving about in the general potential well of the cluster of galaxies. This is a well-known galaxy. In GC 1265, the radius source is called 3C83.1b in the Perseus cluster of galaxies. And because the galaxy is moving about, the jets are bent backwards. On the left, you see a lower resolution image. On the right, you see a higher resolution image of the central part of the galaxy only. All right. The scales are very different. I should have marked the scales. I'm sorry about that. Okay. But what I want you to illustrate is that the plasma gets affected by the ramp pressure of the intercluster medium as it is moving out. And this is something which you see in sources of clusters of galaxies. And these are referred to as tailed radio sources. Depending on the opening angle of the jets, they are called narrow angle or wide angle tail sources. So you can get all kinds of interesting structures. Sometimes there could be both nuclei in a galaxy, which have two galaxies, because in a cluster of galaxies, what happens is that galaxies can merge as well. Smaller galaxies can get swallowed up by bigger galaxies. So you have a whole lot of interesting dynamics going on in clusters of galaxies. And this gets reflected in the AGN or the radio emission or the jets which you see as well. So here, for example, is a source which looks like a head tail, like a fish swimming through water where the plasma has been completely bent backwards. Here there are two nuclei in the same galaxy where the jets are actually intertwined amongst each other, and you have a double nucleus over here. This is one of the very few examples of a binary nucleus in the central galaxy, in a cluster of galaxies. So galaxies, not only the radio emission gets affected, but the radio jets themselves can also affect the cluster medium. Here is an example of that. Here, what you see over here are in white are the radio contours of a galaxy called 3C84, which is again in the Perseus cluster of galaxies, NGC 1275. And, and what you see in blue are the X-ray contours. The yellow being the highest in terms of intensity, and blue, the dark blue being the lowest. And what you see over here is that when you see the radio peaks, not the red dot with the nucleus, but when you see the lobes of emission, where it peaks over here and here, you can see there is a dip in the X-ray emission. So the radio jet is also affecting the environment. It not only affects the environment, but it also affects the galaxy itself, the interstellar medium of the galaxy. So these are referred to as feedback processes. I just want to introduce you to it so that, and this is a very important component to take into role, take into account while understanding the evolution of galaxies themselves. Because if the interstellar medium gets affected either by compressing gas clouds to form stars or heating up the gas clouds, preventing star formation, or even ejecting some of the material out, it has a profound effect in the evolutionary history of any particular galaxy. And this is something which one has to take account of in understanding not only the evolution of galaxies themselves, but the evolution of our universe itself, because these are important processes which is generally referred to by the term of feedback. And my friend Dipanjan talked to you about simulations, and he has been sort of playing a very significant role in understanding how jets affect the interstellar medium of galaxies, particularly low luminosity galaxies, and have come up with a lot of interesting results. Okay, no further questions. Okay, now feel free to put your question in the chat anytime you have a question. Okay, or you can raise your hand and ask as well anytime. Now, I will move on to another topic, but before that, what I've spoken so far, I want to give you a little bit of time to ask any questions you might have. Just 1 or 2 minutes. You've been asking in between, which is excellent, but I also want you to put in if you have any other questions on what I've done so far. I'm going a bit rapidly, but I'm also not trying to get into too much of detail, but just giving a flavor of the physics behind it. Any quick question?
So let me ask one elementary question. I mean, what is this lifetime of these jets? They will be there for so many years, or say for a long period, or say they will soon vanish?
Okay, the thing is that that's a very interesting question. How long will the jets last? Okay, now the thing is that we can only sort of make estimates of that from the observations which we see. So, if, for example, in the largest radio sources, we find that the jets can extend up to several hundred kiloparsec, right? And they seem continuous. They seem to be supplying energy. The jets are clearly visible. Now, if you take a velocity at which the jets are moving of a certain fraction of the velocity of light, maybe 0.2, 0.3, 0.4, 0.5, you'll come up with numbers of millions of years. But that is in particular cases. But there are also cases where the jets seem to be sputtering in the sense that it is probably alive for about 10 to the power of 3 or 4 years, then shuts off for a little while, starts off again. And we will, if we have time, we will discuss a little bit more of about what may be triggering the formation of jets. But the time scale of the jet activity can extend from about 10 to the power of 3, 4, 5 years to about 100 million years or so, right? And this is inferred from the observations and estimates of the velocity of the large scale jets. Okay. There are two things in the chat. Let me quickly get into that, and then we will get into the next topic. Okay. Now, Subrata asked, do the narrow regions of the jets contain only high energy photons? How do they slow down and end in the hotspots? Okay. How do they slow down in the hotspots? Are there any other reason other than movement of source for jets to bend or distort? How do radio waves influence the stellar evolution? Okay, let me go backwards. Radio waves can actually, not radio waves, but not the waves itself, but what is happening is that what you're seeing as radio waves is due to, or radio emission, is due to high energy particles which are moving at relativistic speeds, right? So, for example, imagine that there is a cloud which it encounters. Now, if it's going to compress the cloud, okay, the physical conditions differ, but if it's going to compress the cloud, then it could trigger star formation in that cloud. And there are physical examples of that as well. Okay, now that is one aspect of it. So you could not the stellar evolution. So star formation it can affect. The other way of looking at it is that, for example, which I mentioned about Dipanjan's work, very nice work, which was along these lines, which were initiated a long time ago by Jeff Bicknell, but he's sort of explored a whole range of parameter space in recent years. That when a jet, particularly in a Fanaro-Freiley class 1 source, which is not well collimated, trying to move its way through the interstellar medium of the galaxy, it's going to interact with the interstellar medium, right? And once these high energy particles interact with the interstellar medium, it can heat up the gas. Now, for stars to form, it has to collapse. It has to collapse means it has to overcome the internal energy of the system. Gravity has to overcome the internal energy of the system. So if you're going to heat up the gas, then you're going to suppress star formation. All right. So both the processes are seen to occur, and what occurs or what dominates will depend upon the particular physical conditions. But the jets can trigger star formation as well as suppress star formation. There are examples of both the cases happening. Right. Are there any other reason for other than movement of source for jets to get bent or distorted? The reason is that I mentioned this yesterday, Giriraj, was that jets can get bent by not only the movement of the galaxy, but as I just mentioned, if it interacts with a gas cloud, it can bend it. Just as if you take a water pipe and you hit it against a wall, it's going to change direction. So similarly, jets can interact with inhomogeneous clouds of gas in its medium and get deflected. Some of these clouds can be pretty dense and affect the dynamics. Then jets could be precessing, which will also affect the shape of the jets. It won't be linear. Then also instabilities can develop, which will lead to bends in the jet. Just as two fluid flows, when you flow one flows against the other, you can have development of instabilities such as the Kelvin-Helmholtz instabilities, and that will lead to non-linear jets with shapes which reflects the development of the instabilities. Then Subrata's question: the narrow regions of jets contain only high energy photons. Actually, jets by themselves are narrow, but today we believe that the jets also have internal structures in them. There is probably a faster flowing spine within it, with a slower sheet around it. And this has been sort of inferred from very detailed observations. And so it is not a question of just high energy photons being there in the center or the narrow regions, but I mean, that is something which we know a little better when we can make high resolution images of the interiors of jets at high energies, which we are still not being able to do. The best resolutions we have are with Chandra at about 0.5 RCM resolution. But there is indirect evidence or even direct evidence from radio observations today that there is a more energetic, faster flowing spine in a jet with a slower moving sheet around it. And the jets basically slow down because they're dissipating energy as they go outwards. In the case of Fanaro-Freiley 1 jets, in the case of Fanaro-Freiley class 2 jets, you're also hitting the edge where you're interacting with the interstellar or intergalactic medium, where you will face resistance to the flow of the jet material, and it is going to slow down.
Okay, sir. Thank you.
Okay. Now, are there life cycles of jets? Yes, there are life cycles of jets, Sarvesh. But the thing is that is a very important and an active area of research. What could be the life cycles of jets? And today I'll show you one or two. Yesterday also I showed you an example of two pairs of radio lobes. So clearly the jet has switched off and switched on again. There are many examples of such cases. And in some of our work we have done so far, we find that the life cycles have a large range from about 10 to the power of 4 or 5 years to about 10 to the power of 8 years or so. But what determines these life cycles is something we don't have much of an idea about right now. It's possibly related to the supply of fuel, but that is more of speculation rather than being supported by hard observational evidence. Okay? Right. Now we'll move on to the next topic. How fast are the jets moving? Okay. And as I mentioned yesterday, that we can determine how fast the jets are moving by measuring its velocity. How do you measure velocity? You measure position at one point of time and you measure position at another point of time. You know how much it has traveled. You divide it by the time and you'll get a velocity. Just like when you want to measure the velocity of a car or velocity of any object, right? A velocity at which, they complete a 100-meter race or whatever. So it's a very similar concept. Okay. Now, let's see how we operate it in terms of extragalactic objects. Okay. Now, this is again the jet in M87, which I showed you earlier. And this is the jet in a giant radio galaxy called NGC 6251, which has been mapped on all kinds of scales. And when you ask whether the emission is continuous, how long it lasts, in this case, actually, you can see the jet, which has been blown up into smaller and smaller scales, that the jet is continuous on megaparsec scales almost, hundreds of kiloparsec scales. So you can divide it by a velocity, which we'll talk about in a short while, and you will get that the jet is continuous for millions of years. Now, if I want to measure a velocity, I need a component from which I want to measure a compact component. This is the nucleus of the quasar which I mentioned yesterday, 3C273. This is the core component of it, and this is a knot. These are two particular knots in the galaxy. Now, the thing is that these knots have to be compact because the motion is in the milliarc second scale. Okay. Now, to get an idea of what milliarc second means, that if you were to stand up in, say, Lal Killa and hold up a 10 rupees coin, and say somebody from IUCAA Pune wants to measure the angular size of that coin, that would be on the scale of milliarc seconds. So that's the kind of resolution which you want to try and monitor these motions. The Event Horizon Telescope, which mapped the black hole, that was like putting an apple in the moon, and you're being able to sort of make out the structure of the apple by observing from the Earth. Okay. Now I want to measure this motion. The problem with that is that I can only do this for the nuclear jets, because for the large scale jets, when I observe it, the structures are not so compact, they get resolved out, and you don't see any compact feature at all over there where you can measure the motion of the object. So I can do this for the small scale nuclear jets. Here are two examples, 3C273, which I mentioned. These are old plots, but it doesn't matter, just to illustrate the effect over here. And you can see this component, if I align up the core or nuclear component, then this component is moving out. Similarly, over here, another quasar, 3C279, and you can align up components which are originating and measure the velocities. And when you do this exercise, you get velocities which are greater than that of light. And that was initially quite a puzzle, till it was resolved by very simple physics, actually, a very simple geometrical effect, actually. And here is also superluminal motion in the galaxy M87, Messier 87, which we have been talking quite a lot about. John Beretta and his collaborators have done this, and you can see that you can monitor the motion of this component over here. You can see the component flux density may also change with time, and they infer velocities of 6 times the velocity rate. How do we understand that in terms of basic physics? It's very simple, actually. But the jet has to be coming towards you. Suppose this is the nucleus over here, and this is the blob of plasma which is coming towards you at an angle phi to the line of sight of you. Now, after a time t, the component will appear displaced on the sky, appear to move a distance, vt sine phi. Why is that? That's because we see everything projected onto the plane of the sky. Okay. Now, this is the distance which I will get, and then I have to divide it by the time. And the time would be what? The time would be the detection of the signal when it was over here, say, versus the detection of the signal when it has traveled this distance and it is over here, right? So that is because you're detecting the signal from this blob of plasma when it was at this location initially and at this location later. So if you do a little bit of algebra, you'll find that the distance is Vt sine phi, and I want to divide it by the time, okay? And the time between the two pulses or two signals from when the plasma was here and here can be got by subtracting this Ct, which is the distance traveled by the light when it was from over here, versus minus this, okay, and divided by velocity of light, and that will give you the time which it has taken to travel that distance. And if you do that, I can share the slides with you. I'm going a bit rapidly, I realize that, but you'll come across the expression. This is just simple algebra over there. Beta apparent, where V equal to beta C, the apparent velocity is equal to beta sine phi divided by 1 minus beta cosine. If phi is 0, beta apparent will be 0, because if something is coming directly at you, you are not going to see any motion transverse to the line of sight, and you will not measure a velocity. But if phi is small, so 5 degrees is what I'm taking over there, and the jet is moving at 0.99 c, which is nearly the velocity of light, within 1% of the velocity of light, then you'll get a beta apparent of 6.3, which is going at 6 times the velocity of light. Okay, and physically understand it, you can understand it this way, that you see, because this is moving at very close to the velocity of light, okay, it is almost keeping up with the wavefront which it emitted when it was over here. If it was exactly at the at the velocity of light, you'd have seen no time difference at all, no difference between the wavefront and this plasma. But because it is moving very close to the velocity of light and it is coming towards you, the time which you infer gets squashed by a factor depending upon the velocity at which the plasma is coming towards you. So you're dividing this distance by a very small time difference. So it's a geometrical effect which you will get when a jet is coming towards you at a small angle to the line of sight. So I would like you to just remember this expression, and when I share this with you, just derive it yourself. You'll be able to do it very simply. Okay? So superluminal motion does not violate special relativity, but it is a geometrical effect due to jets moving towards us at a very small angle to the line of sight. If it is moving away from you or at large angles, you're not going to see superluminal motion. Right? It is only when it is moving towards you and the wavefront which it emitted earlier, the radio blob or the jet almost keeps up with the wavefront, so your time is less. So when you get distance divided by time, your velocity blows up to greater than velocities of light. Now, what also happens when a blob of plasma is coming towards you, if you incorporate all the special relativistic effects plus the frequency shift, you'll find that the apparent flux density also gets enhanced, and it can get enhanced by a very large factor, depending upon the velocity and the inclination to the line of sight. Actually, some of these I sort of wrote down in an article for undergraduate students for resonance, so you can have a look at that article as well. Okay, so when it comes towards us, it is enhanced. When it is going away from us, it gets diminished. So what you have is that the ratio of the flux densities is given by 1 plus beta cosine phi divided by 1 minus beta cosine phi to the power of n plus alpha. N can be 2 or 3, is a bit model dependent. With jets, it's usually 2. All right. Now, when I say V is of the order of C, just for argument's sake, phi is of the order of 20 degrees, the flux density ratio is huge. It's 30,000, right? So that is an explanation for why these jets which are coming towards you appear to be one-sided, while the extended lobes appear to be two-sided, because the receding jet is also there, but it is moving away from you with a significant fraction of the velocity of light, not really the velocity of light. The large-scale jets are probably 0.3, 0.4 times the velocity of light, but because they're moving away from you, the flux density appears diminished due to Doppler effects, and you don't see it. But you see the lobe because the lobe is hardly moving at all, moving at very, very low velocities, because the external medium is stopping the jet from moving out like a snowplow going through it. Okay, let me look at the time and then we sort of see. It's 12:20, so we'll take about 20 minutes more. Okay, we will stop at whatever point we stop. All right. Now, any question on that? Any questions on that? That we can measure velocities for the small scale jets, and we infer that the velocities are very close to that of light. We can infer velocities of the large scale Penrose-Riley class 2 jets and also class 1 jets by modeling and invoking these relativistic effects. And we can we get velocities of a reasonable fraction of the velocity of light, but not as high as in the case of the nuclear jets, which are moving at almost the velocity. Okay, so I'll stop for a minute if there are any questions on this so far. Any quick questions? No? I don't know how much time to spend on this, but it's a very interesting test actually. The map which I showed you a little while earlier, right? You can see that a nuclear jet, which is just 1 parsec, points in the same direction as a 100 kiloparsec jet. So if I were to understand this jet in terms of brightness asymmetry of velocities, which I can actually measure if there's a compact component, and understand this asymmetry due to relativistic motion, then it is sort of natural to assume that the large-scale jet asymmetry is also due to relativistic motion, although the velocities may have slowed down due to dissipation of energy and also getting sort of training material from the medium in the case of Penrose-Riley class 1 jets. But can I test this further? Can I make sure that the extended jets are also coming towards us? There's a very interesting test which was done by Robert Lang and Simon Carrington Simon Carrington is part of his PhD work. Robert Lang initially thought of the idea, and that was as follows: that if I have a galaxy similar to the one I talked about over here earlier, say let me say this is the nucleus of the galaxy. One jet is coming towards me, one jet is going away from me, but the galaxy has a magneto-ionic medium around it, right? Magneto-ionic medium around it, and the emission from the receding lobe will go through the magneto-ionic medium of the host galaxy, whereas the one which is approaching us will either not go through it or experience much less of it. Now, when linearly polarized radio waves from the receding lobe will go through the magneto-ionic medium, the E vectors will get rotated, and once you rotate the E vector, because of the irregularities in the medium, they will get rotated by different amounts. For example, if they were all aligned initially, they will get rotated by different amounts. And when you observe all this within your beam, it will lead to a net decrease in polarization. So the receding lobe would be depolarized compared to the approaching lobe. And that was what was done by Robert Lang and Simon Carrington. This is a map of a quasar, 3C47, and this is at high frequencies, and this is at low frequencies. And the amount of rotation which you see, or the amount of depolarization, depends on the wavelength of the radiation, because the amount it rotates is proportional to the square of the wavelength. All right? Proportional to the square of the wavelength. So at low frequencies, it is going to depolarize. And that is what exactly they established to show that at least the jets are on the approaching side, to show that their asymmetry too is possibly due to relativistic motion. It is at least a consistency argument here. So the approaching sort of lobe is not depolarized at all. What is plotted over here is a ratio of polarization at 20 centimeters versus polarization at 6 centimeters. And you can see these values are high over here, whereas it is very low on the receding side. So the observed jet is on the approaching side, consistent with relativistic beaming being the logical explanation for the asymmetry of the jets. More detailed modeling for FR1 jets, Penrose-Riley class 1 jets, also suggests that. Okay, so we will stop with that argument on velocities of jets. So any quick questions on that, I can take it, and I'll spend about 10 or 15 minutes talking about supermassive black holes and the relationship of black holes to jets, and then we will stop this 2-lecture series. Okay, but any questions on velocities of jets? We can take it up.
question is that you explained the approaching and receding, but still I have one question regarding that why, what is the reason we take the relativistic beaming model ratio? Can you explain it again?
Relativistic beaming model ratio. Okay. Now, if I first let me just try and understand this. Okay. Now let me take this jet over here. Okay. This is a quasar 3CR47. Now I have two lobes of emission on opposite sides, right? Which are reasonably symmetric, isn't it? And then I have a jet, and then I have a signature of energy supply, which is to only on one side, right? Now, the natural question I'm going to ask myself is that why is it that the external emission is two-sided when the energy supply appears to be one-sided? If the energy supply is one-sided, then why is the source symmetric on large scales? If the source is symmetric on large scales, then it is natural to assume that there must be energy supply to the opposite side as well, right? Energy supply to the opposite side as well. Then the next question I'm going to ask myself is that why is it that I'm not seeing the jet on the opposite side? I could say that, okay, the jet supply is one-sided at a time and it keeps flipping, all right? There are issues you'll run into that to match up the time scales as well, although efforts have been made to do that. But relativistic beaming, where the approaching emission is Doppler boosted, provides a natural explanation for it. It provides a natural explanation for superluminal motion, where you can actually measure the motion and get velocities which are very close to that of light. And both superluminal motion, jet asymmetry, and its correlation with the depolarization asymmetry are all consistent with the jets moving outwards at relativistic velocities. Now, if this explanation is correct, then let me say that the jets on the opposite side are much weaker. Then I can test it also by trying to make observations of much better sensitivity, so that I can go much deeper and ask myself, can I see the opposite jet? And in some cases where I have been able to make observations which are much deeper, I can pick up the counter jet. Okay, so relativistic beaming provides a natural explanation for the asymmetry of the jets, and the jets intrinsically have to be symmetric. You might also argue that momentum has to be conserved when material is going out from the nucleus in opposite directions. But the fact that there are two symmetric lobes on opposite sides suggests that the energy supply is likely to be symmetric. And then we find that with the whole gamut of observations, that relativistic beaming provides the most natural explanation. Although there may be cases where there is some degree of intrinsic asymmetry, but overall, that relativistic motion provides a natural explanation. Is that okay?
Yes, sir. I got that. Thank you, sir.
Okay, you're welcome. Okay. Now we'll spend a little bit of time looking at initial arguments of why we need supermassive black holes. Okay. Okay. So I'll probably take about 15 or 20 minutes to round off. So I hope you're not too hungry. Okay. I know it's been a long day since morning, but it's okay. Right. So let's look at why we need supermassive black holes and what is the evidence for that. I'll only talk about AGN. I will not talk about stellar mass black holes over here. Okay. Now, what is the evidence for supermassive black holes? We talked about yesterday, some of you correctly mentioned that objects would be closer to the massive black hole, would be moving faster. So if I just put in, basic Kepler's laws kind of thing, an approximate version of it, and I try and make an estimate of how far these line-emitting clouds are, I will get a supermassive black hole at the center. I can also infer that such massive objects must exist from the variability arguments. Okay, I mean the nuclear emission, particularly at high energies, are variable on a range of time scales. Here, one is showing the variability for the quasar 3CR279, whose superluminal motion you saw earlier. And particularly if you go to high energies, you'll find that there are often scales of variability which are much smaller than, for example, at radio frequencies. At radio frequencies, it also varies, but usually it is on much longer time scales than, for example, at X-rays or gamma rays. Okay, this is at greater than 200 MeV in the largest ray. Now, for example, if you're going to see coherent motion, variability, then you need some blob or region to be emitting or going up and down coherently. If that region all went up and down randomly, then you would not see the kind of variability which you're seeing over here. So to vary coherently, you need a you need a signal to be transmitted, and the maximum velocity at which it can be transmitted is the velocity of light. So you can take the Schwarzschild radius of a black hole, which is related to just a mass, okay, divided by c, and get an estimate of how time may be related to the mass of the object. Okay, because Schwarzschild radius is the sort of measure of the event horizon of the telescope, of the of the area around the black hole. Okay, and from the shortest time scales that you get, you can go and estimate what the mass of the object is. And if you do that, you also get million solar masses. And there is rough agreement, at least, between estimation from the broad emission lines and from the causality or variability arguments. Now, once we sort of realize that there must be a black hole, today, of course, we have an image of the black hole in MH7, but these were some of the early arguments which were used. We find an accretion onto a black hole, which Rajiv has talked to you in great detail, so I will spend very little time on it, provides the most accurate or most efficient way of getting energy to supply the huge amount of energy which we see, 10 to the power of 60 ergs, energy going out to 10 to the power of 45, 46 ergs per second. So what is the most efficient process that we can think about? And it appears that accretion onto a black hole, accretion onto a compact massive body is the most efficient way of doing it. Okay, I've just written down the expressions which you can go down go through in greater detail when I share the slides with you. It's just a proton falling from infinity, and it hits a hard surface. When it falls from infinity, potential energy gets converted to kinetic energy, and when it comes to a sudden stop, then that energy will have to be dissipated, and some of it will go away as heat, some of it will radiate away as heat and power the X-ray sources, which Ranjiv talked to you about. You can calculate the luminosity by looking at the rate at which energy or mass is being accreted onto this compact object. And when you look at the efficiencies of it, you'll find that for a white dwarf, which is more massive, solar mass object, much larger, it is modest. If you get a neutron star solar mass object only about 15 kilometers in diameter, it becomes more efficient, much more efficient than the generation of nuclear energy in the sun, which is only about 0.7%. This is 0.1 is about 10%. And we should be able to do even better when there's a black hole. But black hole has no surface to it. So as Ranjiv explained to you in great detail, that it forms a disk around it. And when you look at the efficiencies for a Schwarzschild black hole, which is a non-rotating stationary black hole, versus a rotating black hole, you still find that the efficiencies are quite good. Okay, rotating black hole particularly goes up to about 42%. So this becomes a very efficient way of extracting energy. But you can ask yourself, can I go to very large luminosities? Is there a limit to the luminosity, or is there no limit to the luminosity? There is a limit to the luminosity, because once you generate photons by accretion, the photons are also going to exert pressure on the incoming material. And the pressure and the material would usually be ionized. So the photons would interact with the incoming material by Thomson scattering, and you have to equate the radiation pressure with the gravitational force or equivalent pressure. And when you match up these two, okay, the inward gravitational force with the outward force due to radiation, you will come across a maximum luminosity which can be achieved, and this luminosity is referred as the Eddington luminosity. You can it's a very simple calculation, so you can do the calculation yourself. All I want you to realize is that accretion, spherical symmetric accretion, provides a maximum luminosity of Eddington, which is called the Eddington luminosity, which is 1.3 into 10 to the power of 38 m upon m sun ergs per second. So, for example, if you had an m to the power, m is about 10 to the power of 8 or 10 to the power of 9 solar masses, that is 100 million or a billion solar masses, the maximum energy you can get out of it is about 10 to the power of 46 to 10 to the power of 47 ergs per second. And these values are consistent with what we measure, both for stellar mass black holes as well as supermassive black holes. From the accretion disk, you can also try and estimate the temperature by equating the luminosity using the Stefan-Boltzmann's law to the Eddington luminosity, and then you can get an estimate for the temperature. And when you do that for supermassive black holes or solar mass neutron stars, you'll find that the solar mass neutron stars is about 10 million, 10 to the power of 7, which would be 10 million degrees Kelvin. Whereas when you go to supermassive black holes, it's actually lower. And the reason why it is lower is because the region from which the emission is coming, the Schwarzschild radius, would be much larger for a supermassive black hole. And this particular temperature of about 2 into 10 to the power of 5 K will lie in the ultraviolet region of the electromagnetic spectrum. And that is why when you look at this is plotted as nu L nu over here, where the luminosity is multiplied by nu, you get a bump, which has been interpreted due to a major contribution from the accretion disk, which is being heated up, which is hot just because of the structure of the accretion disk, which is in gravitational sort of hydrostatic balance. Okay, so this is the kind of structures. I'm not getting details of accretion disk, where Ranjiv has talked quite in detail over there, but just to illustrate to you that how we actually infer temperatures by very simple calculations. You can do more detailed ones as well, but to get a physical idea, and how comparing it observations gives you evidences for existence of black holes as well as disks surrounding them. And I'll just give you one or two results and then we will close. Okay, that people have tried to explore the relationship between the jets and the accretion disk itself. What they have done is they've tried to get jet power or jet luminosity as part of the as an indication of the emission which is coming out, and the emission and the power of the accretion disk itself by looking at the narrow line luminosities. And this has been done by in a variety of ways, by looking at the jet and the disk connections which are related to the black hole. And this is one of the early works which was done by Steve Rawlings and Richard Saunders to say that jet power and narrow line luminosity. Narrow line luminosity is because the photons from the disk are ionizing these clouds, and that there is a connection between jet power and accretion disk. And I'll not get into too much of detail of this, but so this has been also investigated using X-ray luminosities. Here the radioluminosity is connected, the X-ray luminosity, and the mass of the black hole. And so that these are all intimately related and seem to be having relationships which are referred to as a fundamental plane of black hole activity. This was some work done by Maloney et al. And recently, it has also been explored by Payaswani Saikia, who was earlier at St. Stephen's in Delhi, and now she's working abroad using the optical sort of O3 line luminosity as well. So the radioluminosity, the narrow line luminosity, the mass of the black hole, they all seem to be very closely related, forming a relationship suggesting that these are all intimately related, forming what is called the fundamental plane of black hole activity. Now, I will close by just addressing one question, which was asked, that what leads to the formation of the jets, and then we will stop. That one of the very early suggestions to suggest that, well, you really need massive black holes to form these jets. And then Ari Lawar actually plotted this. He plotted a parameter called radial loudness, log R, which is the ratio of the 5 gigahertz flux density at radio versus the optical flux density at 4400 angstroms. Okay, and he said all those which are greater than a factor of 2 are radio loud. That means they have very strong or prominent radio emission. And he plotted that against the mass of the black hole. This is in log scale. So he found that anything which is greater than 10 to the power of 9 has a massive, is radio loud, is greater than 10 to the power of 2. Anything which is greater than a few times 10 to the power of 8 seem to be are less than about 1 or so. So they're not strong in the radio. And there's an intermediate range where you find radio loud as well as radio weak or radio quiet objects. So what this tells you is that mass seems to play a role, okay? But it's not a whole story. It's not a whole story because there is a range where you get both luminous radio jets as well as ones without jets. So, what could be the additional factor which is influencing the role? Okay, let me not get into too much of details of this. Okay, the additional factor which could be playing a role is spin of the black hole. That was what was suggested. I'll not get into details of models. Okay, is the spin of the black hole. Now, there also it ran into some problems because if the black hole is maximally rotating, that means rotating at its maximum possible value, then the 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 region from which you can extract energy actually decreases, so you can get more energy out of it. That is how, for a rotating black hole, the curved black hole, the efficiency is about 42%. So then one can say that okay, these sources, you need both mass as well as spin of the black hole. But that also run into problems because there were objects which were very radio weak and which seemed to be rotating very rapidly. This is a spin parameter with a maximum value of 1, and these are pointed out by Iwasawa as well as Ian McCarty et al. So both black hole mass, but spin alone is not adequate. So, but these are low black hole masses. So one begins to speculate that perhaps it's a combination of both high black hole mass and spin that is required to produce these jets. But again, just black hole mass and spin will not do because you need mass to be accreting onto it. So it's possibly a combination of black hole mass, black hole spin, and the availability of fuel. How it is accreting matter? Is it cold gas which is formed due to accretion of due to interaction or mergers of galaxies, or is it just a hot gas in the general interstellar medium which is cooled or which is cool and is being accreted? So I think the generation of these jets has to do with both mass as well as spin and the availability of fuel. So we need to be able to measure spin accurately for more number of objects more directly. It's not an easy job to measure directly. I'll not get into how you measure it. Some of these measurements have been made by looking at the X-ray line profiles, FEK alpha line, which Ranji would have talked to you about. But these are challenging observations. But today we are on the threshold where we should be able to make these observations with the next generation of telescopes and be able to say more firmly as to what is it that is responsible for the generation of these radio jets. Some also sort of speculate that just like X-ray binaries, all galaxies may be going through phases where they are radio quiet or weak without jets, or weak without prominent jets, and they're strong with prominent jets. We don't know the answers to these at all today. But these are areas which are really in the frontiers of research, and we should be able to make significant sort of improvements in our understanding in the next decade. So I'll end it over here, and we can have a few minutes for questions, and then we'll stop. Okay. Okay. Yesterday, actually, just at the as the everyone in meeting, as the meeting was being switched off, ended, somebody put a message in the chat asking my email address. So you can send it over here. Okay, I'll just putting my email address over here at IUCAA.in. Yeah. So if you have any questions which are very pressing, which may occur to you later, then you can email it to me. I'll either respond to it or I will address it while giving you a lecture on the Milky Way. I'm scheduled to give you a talk on give you an overview of the Milky Way next week, I think, and then I can address it. But I can also respond to you individually, depending on the availability of time, etc. So now we can spend a few minutes asking any questions. I know that the latter part I went through it a bit more rapidly. You can go through the slides more leisurely, but I wanted to just give you a preview of where we are and also respond to the questions which you asked. Okay. So any questions, you can put it in the chat or raise your hand and ask. No more questions? No? Okay. Okay, then we will stop and wish you all the best and see you next week. Okay, what makes Amit Kumar Pandey asks is what makes black hole to spin? Actually, what happens is that, everything in the universe has a certain angular momentum associated. Okay. And a black hole, for example, neutron stars, are formed by the collapse of a massive star, uh, okay, but not as massive as it gives rise to a black hole, right? So the thing is that the star will have an angular momentum when it forms, okay? When it forms, neutron stars, we can measure it directly from the pulsar periods, for example, okay? And neutron star rotates, the fastest rotation is about 1.3 milliseconds is a period. So the thing is that the formation process itself would give rise to a certain angular momentum. When a star is collapsing, angular momentum have to be conserved, and it is going to spin faster and faster. As far as the massive black holes are concerned, okay, I'll come to Shubhadeep's question in a little while. Okay, that that so what was I saying? Yeah. So the thing is that so angular momentum is something which is natural to occur. It will have to be conserved. And just as in the pulsars, we see effects of it directly, but in black holes we can't make the direct measurement as well. But clearly, it is the most natural process for it to be actually spinning rather than non-spinning. And that is and for some of the measurements which have been made, show that the black hole is spinning. So one thing is, and it is related to the formation process itself. Okay. And Shubhadeep has asked, in the luminosity model you have just shown previous 2 slides, is that like torque luminosity modeling? Is that indicates frequency evolution like you get for pulsars, timing analysis? Not quite actually, because here your source of energy is due to accretion. Okay. Whereas pulsars, that is not the case, right? The rotation energy which is being converted into other forms that you see over there. So here it is accretion which is the primary source of energy, and how much energy you get out of it will depend upon the physics of what is going on right in the nuclear region. And when you have a massive black hole which is rotating, then your efficiency of conversion is much more, and you can get more energy out of it. Amit Kumar, as black hole is formed by a star and it has magnetic poles, then why black holes don't have poles? See, when you form a black hole, today as we understand a black hole is just characterized by charge, mass, and angular momentum. Okay, you lose all information once you have material within the event horizon. We know nothing about it. Okay, so what we study or what we get is from outside the event horizon. So okay, this is the Occam-Razor theorem or whatever you want to call it. But basically, when you go inside the black hole, there is no information that is written. You can throw books, spaghetti, your encyclopedias on it. We don't have any information once it goes beyond the black hole, beyond the event horizon. Okay. But we can have magnetic fields threading it, but it's not the kind of pole which we talk about in the case of magnetic dipole or the pole of a neutron star. Okay. Okay. Any other questions? Okay. Okay. You're welcome. And if there's any specific small thing you want me to sort of speak on when I talk to you about the Milky Way, then let me know. Or I'll try to respond to you. But if it's a more general question, then I'll do it in class. Otherwise, if it's a specific question, then I will just reply to you. Okay. So enjoy the rest of the school, the rest of the week, and I'll see you next week. Yeah. All the best. Bye. You're welcome. Bye.